All right, hello everyone. First things first, I just want to say I really appreciate everyone for coming to this. There's a lot of people in this room right now, so thank you all for coming. My name is Scott Coates. I'm an environment supervisor at Rodeo FX. I was the environment supervisor on Dune Prophecy, so today I'm going to be presenting Shaping Light, Shaping Worlds, the role of Karma in Dune Prophecy. So who are Rodeo FX? Rodeo FX are a multi-award-winning, mid-sized VFX company founded in Montreal in 2006 by our CEO, Sébastien Moreau. Since then, we've opened up many studios across the globe, Quebec City, LA, Toronto, Paris, and in 2025, we acquired Micros Animation. So what type of projects do we work on? You can see here we've got an array of different projects, old and new. You know, some of my personal favorites here, Paddington 2, Golden Compass, Indiana Jones, and what we're going to talk about today, Dune Prophecy. So I'm just going to play the company breakdown of Dune Prophecy. Every single shot you see here was rendered in Karma, mostly Karma XPU.
Fremen don't stand a chance against us.
I hear you slaughtered many Fremen on Arrakis.
We need to defend our values with ferocity, pride.
All right, so I'm going to quickly just talk about the agenda for this. I'm going to first touch on the environment creation, overview, project methodology, and then a bit about USD. Then after that, move on to Karma, our motivations for using it, look dev, lighting, rendering, compositing, and then a few production tips, best practices at the end. So the project overview. We work mainly on the Imperial Palace environment. We see this in several episodes of the show. There were 94 environment shots, a mix of exteriors and interiors. We also rendered crowds, vehicles, and props to composite with both live action footage and this CG environment. And all shots were rendered in Karma XPU, with Karma CPU being used for fog and atmospherics, so uniform volumes. The environment was nominated for a VES Award in Outstanding Environment in an episode, commercial, game cinematic, or real-time project. So what was our methodology on the show? We were going to create, light, and render the environment into shots using a small generalist team. We had a strong collaboration between the assets department, so modelers, texturers, and look dev artists, and then these generalists that rendered the shots. We rendered shots as full frame range sequences or single frame overscans and spherical panoramas, like where it was appropriate when we didn't have much parallax. And then we wanted to create complete images in CG. What we see in our renders shouldn't be visually too far away from the final comps in Nuke. Our interior shots were actually built by the assets department and rendered by the lighting department, whereas the exteriors were all by the generalists. So when we first started building this environment, we broke it down into 4 main sections. The front garden in red, the palace there in green, the back garden in blue, and then the outer landscape in orange. So the main palace itself, the main building of the palace, was actually built by the assets department. But we did make an assembly for it because it had lots of dressing, extra things that the generalist could add on top. And then the outer landscape is basically like all the terrain, all the cliffs, the ocean. And then the 2 gardens are like the kind of regal gardens in front and behind the palace. So before I move on, I just want to talk about the concept of a USD layer stack. So in our pipeline in Rodeo, we're full USD and Solaris. And most of our assets, like characters, props, and even some environment stuff like buildings, this palace, for example, that was built by the assets department, it came as a layer stack. So a layer stack is basically when you take the layers of each department, stack them on top of each other, and then you get a file which has like the geometry coming in first, and then the textures overriding that, and then the shading overriding that, and then you just have a full asset that you can import into your scene and render. So that's a layer stack. But for our USD environment assemblies, we didn't actually want to use layering because when you start making an environment out of layers, you end up with a load of dependencies. So what we decided to do for our assemblies is we kept them as a single USD layer that references other files. So we didn't do any stacking. So for example, you could publish a geometry somewhere for like the garden walkways or the terrain. You could reference that into the assembly. You could do a point instancer, publish that, reference that into the assembly. The prototypes of the point instancer could be a layer stack, but they could also just be like a random geometry. And then you could also reference layer stacks into our assembly. So everything is just a list of references. When we first started building the environment, we make a dev shot and a dev cam. And what that is, it's basically just like an environment outside of any shot context, where you just point the camera in different directions that you might have in the final production. So here you see like we've got some wide views of the palace, we've got some views kind of closer in the gardens, we've got some views looking out to the ocean and the cliffs. And this is only kind of 9 of the frames, but the full camera was, I think it was 24 frames or something. And we'd render that every couple of days and just see how all the assemblies are progressing. We also use the Karma physical sky for this as well, like throughout the whole show, to keep the lighting uniform. So Karma, why did we use Karma? It's a first-party render inside of Houdini, so we get unmatched interoperability with like Houdini and Solaris. XPU allows us to utilize both the GPU and CPU farm. So we have like a lot of blades on the render farm that don't have good GPUs, so we can utilize those. But then we have a small pool of machines that have really good GPUs with a lot of VRAM, so we can also utilize those with XPU. We really wanted interactivity during look dev and lighting process, especially when an artist has a decent GPU on their workstation. And then the most important thing, we wanted to gain some production experience using an XPU engine, because we've never done that before, and we want to know like the best practices. So at first, we set out kind of with a conservative mindset to just use Karma CPU, but then we found that XPU was just better for most cases. It's faster in general if you don't need advanced sampling, even if you're using a CPU. Our Karma Fogbox pass, so our uniform volumes, we did render those in Karma CPU because that engine has screen door samples, which allows you to really reduce noise and volumes. We decided to shade only in Material X context, so that it works with CPU and XPU. For those that don't know, if you shade in a VEX context, you can't use Karma XPU. And then we use Intel Open Image Denoiser on all passes as a post-process to remove the last bit of noise. So I'm just going to quickly talk about look development. So the first thing that you need to do when you do look dev, you need to be able to load textures, right? And in our pipeline, the way that texture loading works is the texture paths come in as primvars on the assets. So for example, you have all these megascan cliffs here, and each cliff, it will have a path as a primvar, as a string primvar, to tell the renderer where that texture needs to be loaded from. Unfortunately, in Karma XPU, you can't load string primvars in the shader. So you see here, I've tried to do it. I've got a string prim var. I've assigned it to these cliffs. Everything's going red because it's using that red fallback texture. So we had to make a workaround for this, and this is a bit of kind of pseudo code. I'm just going to describe the process. So you have to create a material and make a string parameter as the placeholder for a texture path. Plug this parameter into the file path of the texture node. Assign the material to some prims like you usually do. And then for each set of prims where the material is assigned, for each subset of unique texture prim vars found within that shading assignment, you reference the material using inherit to make a copy of it. Then you replace the texture paths on the parameters of the copy with those unique values, unique texture prim var values, and then you reassign that copied material. So it sounds complicated, but what you end up with is for each unique set of texture prim vars, you have a child shader, kind of similar to how it works in a game engine, and the child shader has the baked-in texture path. So instead of resolving the textures at render time, you resolve them in Solaris time, in the scene description. And it works the same way as it would in Karma CPU. You just have to put a HDA after the shading assignment. So once we could load textures, our asset department could basically go ham after that. Like they could do whatever they wanted, you know, same as any other render engine. So here you see some examples of some of the things they built and lookdev. Like the main palace itself, the assets department, they built that, and you know, they use a lot of cool techniques. Like a lot of that palace was actually built out of instances, both point instances and instanceable references, and a lot of procedural techniques as well, like the hex triplaners, the noises, all the, you know, the standard procedural stuff. And they also lookdev the vehicles, the suspensor car, and the crowds as well. The terrain, however, was built by the generalists, and this was kind of a mix of Houdini height fields, SOP, post-processing, megascan kit bashing as well, like bashing in instances into the side of it, and it was all fully procedural shaded. We used, like, again, the same stuff, hex triplaners, noises, world positions, and we even used the Karma point cloud lookup, the one where you can load a BGO file, give it a point cloud to, like, shade certain areas in certain ways. We use that for, like, pathways and, like, where the water hits the cliffs. For our trees, the one thing I wanted to mention about our trees is all of our trees in Rodeo, especially on this project, they were nested point instancer. So there's no opacity map on the leaves. The leaves themselves is just a geometry. Like the leaf model is a geometry, and then the tree contains a point cloud of all the transforms of the leaves. So this means we don't have to use any opacity maps in the shader. And it's really, really memory efficient. You don't get artifacts like you do with when you use like opacity, and super memory efficient, super fast to render in Karma XPU. And I kind of recommend you do this if you want to do trees. Vegetation, kind of a similar situation. We use a lot of nested instancing for leaves and blades of grass and stuff like that. The key point here is we just use a lot of prim vars in the shader. So all of our shaders, we try to have one shader for most of the vegetation. So, you know, like a grass shader, a bush shader, and then prim vars override the stuff. Instead of having like a million different shaders, we just have one, and we have like different levels of point attributes that we promote to prim vars. So you can see like every blade of grass is a unique blade of grass as a prim var. And then like those wavy patterns on the grass, that kind of motif that the client wanted on this show, that would also be like a point attribute. But the shader's the same for all grass on the show. For our water, we made extensive use of the Karma Ocean procedural, and that wasn't just for the ocean, it was actually for the water pools in the gardens as well. The water planes were published as part of the assembly, and then they were LOP imported into the ocean procedural, because you need a SOP geo for that. And then changing the ocean looks was really easy because you could just swap out the spectra file on a shot-by-shot basis. So on the left there, you can see we're trying out different looks in the same shot just by swapping the file. And then on the right, you can see like the difference between the ocean water and the garden water, but both of those are using the ocean procedural. To take our water to the next level, we dressed in some algae. And again, you're going to notice a trend here. Like that was another nested point instance. So, you know, the smallest atomic piece of that algae, it was like a single clump of like, you know, whatever it was. And then that gets scattered around to make a noisy patch like you see in the bottom right. Then you take those noisy patches, you copy those everywhere, and you get so much coverage and memory efficiency out of that. It just really improved the look everywhere. For our architecture, we used a lot of instancing for this as well, like our pathways, our pillars, any statues that we're repeating, any kind of any features that we're repeating, we tried to leverage instancing as much as we can to save on our memory. All the shading was procedural. Nothing really textured by hand, barely any UVs, honestly. And a cool technique that we did is, as because we're working as generalists, every time that we see, a piece of architecture in a shot that wasn't really up to scratch, we'd kind of just like call it out in the shot and say, okay, this one, we need to add a motif to it. We need to add like a wavy pattern, or you can see on the bottom right, some sort of wavy kind of geometrical detail there, and it adds quite a lot. You just add that and you add a few prim bars and you're good to go. We have a kind of a uniform concrete shader. So another cool technique that we did is we did a technique called recolored albedo. So what that is you take any texture map. Here you can see like any texture map with a kind of a uniform value to it. Here you can see like a megascan, I think it's a rock texture. You divide it by its average value. To find the average value, you can use a curve tool in Nuke, and then you get the uncolored texture, which is basically the texture divided by the average value. And then what can you do with that? You can multiply that uncolored texture by any arbitrary color, and then you've basically recolored your texture. So why is this useful? So on the left here, on the top, you can see the raw megascans that were ingested just from the megascan download. And it's very subtle, but you see there's some slight hue, saturation, and value variations in there. So if you were to bash all those instances together, you might get a bit of a mishmash. So on the bottom, you can see that we've basically recolored all those textures, like uncolored those textures, and then multiplied that by like a sandy color, and it just makes everything a lot more homogeneous or uniform. On the right, you can see a more severe example with like a cyan or a turquoise color, but you preserve all those hue, saturation, and value values from the original texture, but you can have any color you want. So here you see a result of that, like all those cliffs kind of bashed together, looks kind of uniform, but you can see in the little picture-in-picture there were actually many different models from Megascan. So for our lookdev pipeline, lookdev for all of our hero assets came baked down into the layer stacks that I described at the start, so like assets from assets department. The environment generalist lookdev, however, was contained within HDAs that loaded into our shot rendering scene, so actually nodes and assignments in the scene. Loading that lookdev as nodes keeps it live and allows us to make use of wildcards to assign shaders, because in USD it's static. So now I'm going to talk about lighting and rendering. So for all of our daytime shots, we started off every single daytime shot just using the Karma physical sky and the Karma fog box. This is really cool because it gives us a really good starting point. You get a really realistic photographic exposure from it. All you have to do is like change the azimuth of the sky, change the turbidity of the sky, angle your light, and then you can increase and decrease the density of your fog, and you just get looks for shots super quick. So we're basically like for every shot, just do one of those. And then, once that's approved, we're gonna lock that in and then switch that out for a more traditional HDRI and a key light. But we'd still use the Karma fog box in the final render. So here's a result of that. We have 6 shots here. Every single one of these shots started off as a Karma physical sky and then evolved into like your more traditional IBL, HDRI technique. We also use Cloud Gobo Blocker Geo for the, the cloud shadows. But yeah, that's it. Karma fog box, HDRI, and Cloud Blocker Geos. For the nighttime lighting, it was a lot more involved because we had hundreds of different lights. We had lots of spotlights, area lights, and we also used a lot of IES lights to kind of get that shaping that we needed onto the palace and the architectural features. So this one was hundreds of lights and a lot more challenging to render. Yeah. Another cool thing we did for not just for the night shots, but for the whole show is, any time in our models where there was a lampshade or a light fixture, we'd have a really nice automated way to basically just extract that out and make an internal light geo. I think it was it basically was done in SOPs in the end, but it was through Solaris. And you can basically make, a nice light, a nice internal geo that you're going to have as emission. You can set up all the light linking in Solaris, and basically, you can view that live in your viewport with Karma XPU, which I think was really cool. We rendered a lot of panoramas on the show, so like lat long renders, and these are really cool because you render one of these lat longs, and it gets rid of a whole sequence basically. Like here, you can see the nighttime lat long for the lip environment. We didn't actually render as a spherical render. We rendered as what we call a 6-pack, which is six renders, 6 orthographic cameras that represent a cube. And then we take those renders into Nuke and then we stitch them together. And that works with Karma XPU. So it's cool because, like shots like this where there's not much parallax, it's just like over the guy's shoulder or looking out towards the ocean, nodal movement of the camera. You can render one of these renders and the whole sequence is gone basically. Like it's just comp after that, which is really cool. So I want to just talk about our like lighting and Solaris template pipeline. So the first concept I need to introduce is the concept of a chunk. And all it is, this is in our pipeline, it's basically a network box that you can publish. So you can publish it to the show, the sequence, the shot, wherever you want. And you can also embed HDAs in there, which is a really cool feature. So here's the environment rendering template. It consists of 5 different chunks. We had to because we're swapping on this project, I didn't mention earlier, but like all other projects in Rodeo at this time, we're using Arnold. This was the first one swapping to Karma, so we had to change the template quite a lot. So this was the kind of new template that we came up with. So at the start, we have our global settings chunk, which is render settings nodes, camera resolution, overscan, stuff like that. After that, we have the pre-tweak. This is any edit to the scene before the look dev and lighting is applied. So normally we use this for kind of animated tree variants and stuff like that, setting variants of stuff. Look dev, so this is the look dev HDAs that we spoke about earlier. Light rig chunk, so this is the lights and the light rig HDAs, which I'll talk about in a second. And then post tweak is any edit to the scene after the look dev and lighting is applied. So this is normally used to configure the render path splitting. So here you can see an example of a light rig chunk. And you see there's 2 unique lights. There's the moon and the sky. But then after that, we actually have the HDA. That's the Imperial Palace nighttime light rig. So this is a really cool way of kind of building a light rig because you can have an artist work on a HDA for your master light rig, all those hundreds of lights in the palace. And you can have other artists working on the directions of the light and all the other shots. And then basically the chunk contains the HDA. So you're it's kind of like you're almost inheriting, but you're containing the asset light rig for the palace, and it updates throughout the whole show, which is really nice. We also managed our light rigs in ShotGrid. So we set up our key shots in ShotGrid, and then all of those light rig chunks, we publish them to the key shot. And what it means is that any of the child shots, the key shot light rig is going to build in the template automatically. So at the start of the show, you just got to go through and do all your angles, and then you only do the lighting directions for all of the key shots. And then once that's done, you've got everything you need. And the nice thing about this is you can easily swap light rigs from other shots really easily. So the render layers were done similar fashion, Different shots contain different render passes. These were also loaded as chunks. Render layers were automatically built based on the shot, and they could either be rendered by the artist manually, clicking on the USD render ops to send them, or we also have our automation tool, Diacurie. And what that is it basically, you don't even have to open Houdini. Just from a tool, you can basically, on the farm, build the template for whatever shot you want. It will build in all the chunks, it will build in all the render passes, and then it will send them to the farm, do the renders, and then do the Nuke daily after that. So you just, it's like an auto shot tool. There on the right, you can see the UI that we made for it. So you can kind of set up your frame range, what passes you're sending, stuff like that. And it was all automated. So here's typical render layers for one of the daytime shots. So here you can see there's 4 different layers for the environment, one for the ocean and then one for the Atmos, which is the Karma CPU fog pass. So we rendered a lot of things separately to try and save on memory, especially so we can utilize the GPU more. And we merged everything deep. We merged everything deep except the Atmos, because that was just traditional matte. But this technique was really cool because, one thing you can do is anything that you're not directly rendering. So let's say, for example, you're rendering the ENV main 2000 there, the palace. Anything that's not directly visible to the camera, you can set the USD purpose to the proxy, and you save a ton of memory from that. And not only can you do that with the geo, but you can also do that for the shading. Here you can see all of those layers combining together for the final composite. So you see like all those deep layers, all Karma XPU, the ocean, which is the ocean procedural, and then the Atmos on top, which is a traditional uniform volume rendered in Karma CPU and matted. So here's the same situation, but for a nighttime shot. This one was a little bit more involved because we had FX passes, but the same rule applies, you know, like all the environment is rendered deep, merged deep in Nuke. The FX pass, so you can see there's a little waterfall on the bottom left, and there's Ocean 2000, which is the ocean spray. They were rendered not as deep, they were rendered as, again, traditional 2D matting. Here we have all of the light groups for 2 of the passes in that shot. So you see there's 12 different light groups that comp has control over. This is really useful because in a crazy complex shot like that, comp needs to be able to turn up and down lights. So you see the first 2 is like the moon and the sky, and then the rest is like all the kind of complex light groups of the palace in the garden. And here you see the final composite. So it's, again, same situation, like all the passes rendering deep, and then, you know, all those light groups coming together. At the start of this presentation, I spoke about how we really wanted our CG to match the final composite as close as possible. And I think we achieved that because on the left here, it's the final environment version for one of our shots. Then on the right is the final comp. So comp isn't completely, you know, rebuilding the images. They're kind of just really enhancing them, which is, you know, that's what we should aim for. A cool trick that we did with our AOV setup on the show is we made a few custom AOVs. So this is an example of one of them. And basically this is just an RGB noise that, you know, comp can use to do like an extra cloud gobo on top of the, you know, the cloud gobos we already have in the shot. And the way this works is you just make like a little Material X setup somewhere in the scene with a noise or like any texture you want or anything. And then the cool thing about Solaris is you can take the output of that setup, and then in a Python lop, you basically can connect that output to every shader in the scene, every material to its AOV input. So it means that every shader gets, you know, that shading network as an AOV, and we made an extensive use of that to give comp extra stuff that they needed. All right, cool. So production tips. So if you're using Nuke to do your, you know, your shot and asset review, and you're going to use Karma XPU, it's really important to make some nice burn-ins to show you like the metadata of, you know, how much of the GPU you're using, how much of the CPU you're using. So you see there, this is like our very first test using Karma XPU. Like literally, you know, at the start of the show, it's using Houdini 20, and at the bottom there, you can see the XPU devices. And you can see for this render, you know, the GPU's doing 67% of the sampling and the CPU's doing 32%. And this is extremely useful when you look at your render farm and you can see like what blades are using what hardware. Yeah. So the optics device in Karma XPU is your GPU, and you want to always make sure that you're using the GPU. So if you run out of VRAM, you're not going to be able to use the GPU anymore, and your render's only going to be using Embry, and you're going to be basically what I like to refer to as CPU locked, so only rendering using the CPU. So to avoid this, like, you need to be wary of GPU memory limits at all stages during the production, especially memory not related to textures. So Karma XPU, it will page textures in and out of memory, but it won't page geometry or primvars. So you really got to watch out there. You don't want to add too much geo to your scene. You need to remove unnecessary primvars from all assets in your pipeline. If your pipeline has a ton of like attributes and everything, you might want to strip that back, because otherwise you're not going to be able to utilize a GPU, especially when your scene scales. As I said earlier, you know, if you spill over on that GPU memory, you should consider splitting the scene into multiple passes and using a proxy purpose, you know, for anything that's not directly visible to the camera, if you can get away with it. All the artists should be checking that log viewer pane in Houdini when rendering, because it will tell them if their optics device is failing. Something in the scene might be causing that to fail, even if VRAM is not at its limit. This is really useful because if someone does a lookdev somewhere and causes that optics device to fail, for whatever reason, it could be just a bug, they could publish something that just causes all your renders to just be CPU locked. You want to, this is maybe an unpopular tip, but you want to try to benchmark your renders for the worst case scenario. So, your worst case scenario is you're only rendering on the CPU. Turn off your optics device using the global variable and test just on the CPU, because that's going to be your worst case. You see here at the bottom, we have our final kind of burn-in setup on the show. And the bottom right there, you see it says, it's very small, but it says GPU 0% X4. So that means that render pass, it had, that machine had 4 GPUs on it, but we used none of them. So it's a complete waste of those GPUs. So uniform volumes. Karma CPU was better for rendering uniform volumes because you have screen door samples. Drastically reduces the noise, especially in area or cone lights. You want to render these uniform volume passes at a minimum ray depth, ideally 0, and assign a shader with all lobes set to 0, so like a black shader, to improve performance instead of just matting. You see on the left there is low screen door samples, and on the right is high. You really want to balance that against your path trace samples as well, and you're going to have to find that balance, but that's how you're going to get a clean and fast render. So then the last tip is shading. So if you abuse your procedurals in Karma XPU, that's how you're going to get the insane render time hit. So you want to keep procedural shading as simple as possible. Abusing hex tile triplaners, 8K hex tile triplaners, point cloud lookups, rounded edge shader, if you can use them, but if you use too much of it, the render time is going to explode. Use CPU time AOV to detect heavy shaders and objects in the scene. On the right there, you see we've got the CPU time AOV, which you can render in Karma, overlaid over the beauty. And you see there, the ground is red, which means that it took longer to render the ground than it took to render the trees. So when I see that, the alarm bells are going off, because in my mind, it should be the opposite. So then we need to tell that artist you need to optimize your shader. So as well, you see on the left, we have our 33-minute render of our cliffs. And then we basically took out half the stuff from the shader, and it renders in 20 seconds. And the look is not too dissimilar. So what you have to, when you're using XPU, you should think am I getting everything out of the shader? That have I got too much here? If I pull it back, can I get a faster render time while still having the same look? And then the last thing is be very wary of your shader compilation time. When rendering with XPU and optics. Every single time that you fire up a render in optics, it has to compile every single shader in the scene. So if you have a lot of them, that can be a considerable hit. And the other thing as well is if you unplug and replug nodes in your shader, that's going to recompile the shader, so just be very careful. So to conclude, we had a really great experience using Karma on the project, and we look forward to more in the future, and we're already looking at projects now where we're using it. Many lessons were learned. That's the most important thing, and taught us a lot, not just about adopting a new technology. We were using Arnold on all other shows. On this one, we adopted Karma, and it just taught us a lot about how to adopt a new technology. And next time, we're going to be far better equipped. So merci, everyone, and thanks for coming.
Amazing information, Scott. Thanks for sharing that. We don't have time for any questions. We have to move on, but I just want to say, this is a great example of production tips that have been learned in the trenches through work, through experimentation, through innovation, and it's really, really amazing to see that you guys are sharing that with the community, and thank you very much.
Thank you.